Howdy, and welcome to the National Data Buoy Center. There is something going on in the Northern Atlantic. Hurricane Danielle. It's approaching Europe, and there is already another one quite close to Europe. It's obviously not named. But I have been watching this on Windy. So the one we just watched, Danielle, I think it's this one. This one doesn't have a name, it's not on the map we just watched. And if we just give it a go and watch how they're moving, especially the small one, I focus now on the small one, that there is a similar thing happening on the bigger one as well. But for whatever reason, there's a blackout for a half an hour or something. The whole region got blacked out. But if we zoom in, you can see it's spinning. It has this kind of spiral shape form. Yeah, it's a low pressure system. It spins into this direction on the northern hemisphere, which is by many referred to as the Coriolis effect, Earth's rotation and its effect on weather. The Coriolis effect describes the pattern of deflection taken by objects not firmly connected to the ground as they travel long distances around the Earth. What is the Coriolis effect? The Coriolis effect describes the pattern of deflection taken by objects. The Coriolis effect is responsible for many large-scale weather patterns. The key to the Coriolis effect lies in Earth's rotation. Specifically, Earth rotates faster at the equator than it does on the poles. Earth is wider at the equator, so to make a rotation in 24-hour period, equatorial regions race nearly 1,600 kilometers per hour. Near the poles, Earth rotates at a sluggish 0.00008 kilometers per hour. Let's pretend you're standing at the equator and you want to throw a ball at your friend in the middle of North America. You throw the ball in a straight line, it will appear to land to the right of your friend because he's moving slower and has caught up. Everywhere you play global scale catch in the northern hemisphere, the ball will deflect to the right. This apparent deflection is the Coriolis effect. Fluids traveling across large areas such as air currents are like the path of the ball. They appear to bend to the right in the northern hemisphere. The Coriolis effect behaves the opposite way in the southern hemisphere where currents appear to bend to the left. The impact of the Coriolis effect is dependent on velocity, the velocity of Earth and the velocity of the object or fluid being deflected by the Coriolis effect. The impact of the Coriolis effect is most significant with high speeds or long distances. Weather patterns. The development of weather patterns such as cyclones and trade winds are examples of the impact of the Coriolis effect. Cyclones are low-pressure systems that suck air into the center or eye. In the northern hemisphere, fluids from high-pressure systems pass low-pressure systems to their right. As air passes are pulled into cyclone from all directions, they are deflected, and the storm system, a hurricane, seems to rotate counterclockwise. In the southern hemisphere, currents are deflected to the left. As a result, storm systems seem to rotate clockwise. In the northern hemisphere, fluids from high-pressure systems pass low-pressure systems to their right. As air masses are pulled into cyclones from all directions, they are deflected, and the storm system, a hurricane, seems to rotate counterclockwise. it seems to spin counterclockwise, since we are in the northern hemisphere. Here we have Lake Victoria. Kampala? Yeah, it doesn't say that it's Lake Victoria, but it is. Let me zoom in still a bit. No, they don't tell you. But anyway, that's Lake Victoria. And its northern shore is almost exact at the equator. So everything above this is northern hemisphere. If we go back to our storm system here and zoom in, you notice this rotation. Okay. But if you look close, you can see that there is also opposite direction movement going on, counterclockwise. Because it's a Birkeland current. Birkeland currents, they are made of different, how to put it, shells. One will spin this way, one will spin this way, and the other one will spin again the other way around. And I claimed, or not claimed, weather is entirely driven electrically. Birkeland currents are electromagnetic currents. So if so, the Coriolis effect, which should make it spin in this direction, is only partially true, because it does spin to the opposite direction as well. There is movement going on in both directions simultaneously. Here is probably the easiest to see. Now I go backward, now forward. So the whole structure seems to spin in this direction, but it's very important to notice that there we have also movement in the opposite direction. And if we zoom out furthermore, we have to also understand that this one is connected to another weather system somewhere else, wherever they go, but they are connected with each other constantaneously. So I think there is something going on today in England, weather-wise, France, Benelux, Germany, Spain, Portugal, Denmark, Norway, Ireland, Scotland, Italy. Yeah, this is very interesting. There is like this region here in the middle where there's not too many clouds yet, but it is between those different kinds of weather systems. So there is this kind of, how to put it, exclusion zone or whatsoever. So we might experience some quake activity there. But I think I will leave it here. Got to follow the weather. It seems to be very interesting. There might be very much rain coming in not too distant future. Somewhere around here. Let's draw a drop here. Water. Possibly quite much. But we will see how it will develop. Is it too much or just enough? We will see. If it's too much, They have to shut down the nuclear power plants, for example. And some other things might be much more difficult during and after the event. So be prepared, get some food, clothes, and rubber boots at least. Thanks, bye.